Hello there, this is Shoot Socrates. Welcome to video number 33 for my series in multivariable calculus. This is known as Math 5C at Pasadena City College. So in the last couple of videos, we have been investigating parametric surfaces, and today we are going to create the next kind of integral, and it's going to be a surface integral. Big surprise. So let me review first with you the contour integral of a scalar function that we saw back in chapter 4. So here we are. This is the notation that we use for this kind of a scalar contour integral. Okay, and there were two kinds because your curve could be either on the xy plane only or in space. Okay. And the function represents some kind of a density, perhaps, on a piece of wire shaped like the curve C. Okay, so I will see you on page 273, where we will construct the surface integral of a scalar function. All right, so here we are. Note the similarity in the notation between a surface integral of f of x, y, z and a contour integral of the same function. Okay, so in chapter 4, that's a lowercase s, and that's a curve C. Here we have a capital S for the surface, and also double integral over that surface S. Okay, so as the notation implies, instead of an integral in one variable that we did in chapter 4, we are going to have an integral in two variables. Why? Because a parametric surface has two parameters, u and v, in the parametrization. Okay? So we will assume that S has a smooth parametrization given by x of uv, y of uv, and z of uv, where u and v are from some domain, a region in R2. Okay, so to keep it simple, we're going to make it a rectangle, but in the near future, we're going to allow the domain to be a triangle or a circle or some other region that we know how to set up a double integral for. Okay, so the construction is very similar to what we did for a double integral way back in chapter 2. Okay, so here's our domain. In fact, a lot of this was just cut and paste. Okay, so we subdivide the domain for u, the interval for u, into m equal pieces of width delta u. So the width is b minus a over m. And similarly for v, we subdivide cd into n equal pieces of width delta v. So that's d minus c over m. Okay, so we get a partition of a to b and a partition for c to b. And we have this diagram, which is very similar to what we did in chapter 2. Okay, so here's a to b subdivided into 6 pieces. And here is c to b subdivided into 5 pieces. Okay, so it's like you have a birthday cake and you subdivide it into 6 along this axis, 5 along here. So maybe you have 30 guests. Okay, and each of them will get one little piece. Okay, so this is the domain of the parametrization. So R will create your parametric surface. Okay, and what did we see back in the last section? If you hold one of the parameters constant, you get a grid line on your surface. Okay, so for a sphere, you have longitudinal lines, and you also have latitudinal lines, all right? Constant theta, and you have constant phi, okay? So you get these grid lines on your surface. All right, so here we go. Here's an actual portion of a sphere, and you have these longitudinal lines and these latitudinal lines, okay? So there are lots of little sub-patches on our surface, okay, this portion of the sphere. Okay, so what we're going to do next is, well, how big is one of these sub-patches? Okay, because when we did the contour integral, we wanted to know how big is one of these little sub-arcs in our curve, on our curve C. Okay, so now we are going to zoom in on one of these sub-patches. Okay, where does it come from? Okay, so it comes from one of the little pieces of birthday cake that we saw in the last page. So that's from ui minus 1 to ui to vj minus 1, vj. Okay, so one of the sub-rectangles. Okay, so here it is. Here is one of the birthday cakes, the pieces of the birthday cake. Okay, so the four corners will correspond to 4 points on your patch. Okay, so they're sort of like corners, except the contour lines, of course, don't have to be, the grid lines don't have to be straight lines. Okay, so ui minus 1, vj minus 1 might go to this corner, and then ui vj minus 1 might go to this corner, ui minus 1 vj to this corner. We're not going to care so much about this fourth corner over here. Okay, so we have this subpatch, okay, this kind of bulging surface on the actual surface. We want to approximate the area of the subpatch. Okay, well, we know how to do that because back in chapter 1, we know how to find the area of a parallelogram. Okay, so I hope you remember we used the cross product. Okay, so you have A and B, and notice that the parallelogram that they define, well, is almost the same area as this subpatch on the surface. Okay, so the area of this parallelogram, of course, is the magnitude of the cross product of AB. All right, so here's that principle. Okay, we have two vectors. The area of the parallelogram they determine is the magnitude of the cross product. Okay, so who are these two vectors? We're connecting corners on this subpatch. Okay, so this is the lower left corner. It is adjacent to this neighbor and also to this neighbor. Okay, so we form the vector connecting these 2 points and these 2 points. We have A and B, except we're going to do something very smart to it. Instead of leaving each of these vectors as is, we're going to divide and multiply by a delta something. Okay, so check it out. What changed over here? V stays the same. It is U that changed. Okay, here U stays the same, but it's the V that changed. Okay, so you divide by a delta U, multiply by a delta U. This now looks like a derivative, doesn't it? Okay, except we have a function of two variables. So therefore it's not an ordinary derivative, it's a partial derivative. Okay, so this is approximately the partial derivative of r with respect to u. And then you multiply by that delta u. Okay, similarly, this difference quotient looks like the partial of r with respect to v times delta v. Okay, so because we assume that our surface is smooth, these two vectors are not parallel to each other. When we get the cross product, we won't get a zero vector. We will be able to find the length of that vector, and it's going to be strictly positive. Okay, so here's our main result then. If we denote by S sub ij, our subpatch, then its surface area, which we will denote by delta Sij, is approximately the length of the cross product Ru cross Rv at that lower left corner. Okay, multiplied by delta U times delta V. Okay, now we also know in chapter 1 that the cross product of these two vectors is perpendicular to both vectors. This is going to be important when we get to the last section, what follows this one, where we look for the flux integral of a vector function, a vector field, across the same surface. Okay, so now we are able to complete the definition of this surface integral of a scalar function f. It's a double limit of a double sum, as usual, just like the double integral in chapter 2. You plug in the parametrization of our surface into our scalar function. Okay, this will produce a point in space, x, y, z, so we can plug that into our scalar function. Okay, notice we're using the same representative point because the area of Sij is approximated using the same representative point. Okay, so by the power of the fundamental theorem of calculus, also generalized into Fubini's theorem for rectangles, this double sum of a double limit turns into the double integral. Okay, so u will go from a to b in our inner integral, v will go from c to d in our outer, or backwards. Okay, so Fubini's theorem says they're the same. Okay, you plug in your parametrization into your function, you take the cross product of the two partial derivatives, find their lengths, and then you can integrate. Okay, so notice also how this double integral sort of looks like the single integral for the contour integral of a scalar function f on a curve. Okay, so r of t is still a point in space, okay, but it's only controlled by one parameter, t. Okay, so just like almost every integral that we have defined for a scalar function since chapter 2, this double integral, the surface integral, could be interpreted as a mass. Okay, so here I have a surface, a little omelette bowl. You can whisk your eggs in it. Okay, so we can pretend that we can zoom into a point on the surface, and that corresponds to a u and v on the domain for the parametrization. Okay, so we have like a representative u star v star that corresponds to that one point. Okay, and we have to imagine that I can excise a little patch here. How do I do that? I create a little rectangle on the domain for the parametrization. Okay, I take that little patch, I weigh it on a very sensitive scale, and then I take the mass that I find and divide it by the area of that patch. Okay, and the limit as that patch gets smaller and smaller when delta u and delta v get closer to 0 is the density at that point. Okay, so again, of course, this is a theoretical process. You won't actually be cutting little pieces in here. You ruin the bowl that way. How are you going to use it if it has so many holes in it? Okay, so of course we can go backwards that the mass of that little patch will be the density multiplied by this surface area. Okay, and of course that looks like the definition of our surface integral. Okay, so the mass of our bowl, the total mass of the bowl, will be the double integral of the density function ds. Okay, so of course built into this symbol is the length of that cross product. Okay, if the density is 1, we simply get the surface area of our surface. Okay, so I'm going to do an example with you from scratch in a little bit, but I want to show you what happens when you're dealing with a sphere, okay, because many of our problems will involve spheres because they're easy to parametrize, okay, using, of course, spherical coordinates. All right, so our domain in this example is the portion of the sphere, which is in the first octant. So I hope you remember how to parametrize that. So the domain phi will go from 0 to pi over 2. And theta will also go from 0 to pi over 2. Okay, because we only want the first octant for the surface. Okay, so its density is given, let's say, by this function. We will find its mass and later on its surface area. Okay, so we know how to parametrize this. Okay, so spherical coordinates, we have 4 sine phi cosine theta, 4 sine phi sine theta, and 4 cosine phi. This is the domain for phi and theta, just as we mentioned. So plug in this parametrization into the density. Okay, 3x, so here's our x, 3x, 2y, here's the y over here, z squared. take this whole thing, square it. Okay, so simplify, and it goes over here. Okay. In the last section, we already did the partial derivatives and the cross product. Okay, so this is the answer that we got. We generalized it for any row. Okay, so we had rho squared out here. Our row is 4, so we get 16. Okay, we want the length of that cross product. So we take the absolute value of this scalar. Okay, but phi is from 0 to pi, so the absolute value is just sine of phi. I think we've done that a couple of times already. What is the length of this vector? We also did that in the last section. It's just going to be 1. It's actually a unit vector, a unit normal vector. Okay, so this is the extra factor that we are going to include in our double integral. All right, so here we go. Another lovely integral. We have that extra factor right here. This is the integrand that we got from our density function after we plugged in x, y, and z. Here are the limits. Okay, so it's actually pretty straightforward for a change. We do have a cosine theta, a sine theta here, no theta over here. So we know how to integrate them, and we plug in 0 to pi over 2. Okay, so we get a pi here, we get 1 minus 0, 0 minus 1 over here, and we get something involving sine squared phi and cosine squared phi sine phi. Okay, so we need the power reduction formula here. All we need, I believe, is a u substitution over here, because if u is cosine phi, the derivative is negative sine phi, so the plus 2 pi turns into a minus. Okay, and we have the 1/3 over there. And yeah, we break this up into 2, so that's 5/2 phi, and then minus 5/2. Cosine 2 phi integrates into sine 2 phi, divide by 2, so that becomes 4. We've done this a million times before. Okay, so plug in the endpoints, and we get this answer, 368 over 3 pi. Okay, surface area, you integrate 1 ds. So the integrand that we got over here, we completely ignore that. All we have is the 16 sine phi. Okay, so there it is. And we know how to, first the theta. Okay, there is no theta, so it's just a constant. And we go from 0 to pi over 2. 16 turns into 8 pi. We know how to integrate sine of phi, that's minus cosine phi. Plug in the endpoints, and we get 8 pi, and that might look familiar to you. You may have learned the surface area of a sphere. Okay, it's simply 4 pi times the radius squared. Okay, but wait a minute, our radius is 4, right? So 4 squared, 16 times 4, 32. Why is this? Wait, did I do the arithmetic right? 4 pi a squared. So the a is 4. So you square it, we get 16. Oh, times 4, yes, you get 64. Okay, so why is it only 8? Well, we're only in the first octant. Oh, octant, 1/8. Okay, so 1/8 of 64 gives you 8 pi. All right, here we go. So here's a fresh example. I just thought about it while walking Johannes. I have a triangle with these 3 vertices, and we have a density function given by this, 5x plus 6y plus z. Okay, we're going to find the mass of this triangle. Okay, area is boring. Okay, we already know how to do that in chapter 1, right? Take the cross product and take half of that. Okay, so let's go to GeoGebra and look at this triangle and see the best way to integrate. Okay, here are our 3 points. I already made the polygon right there. And yeah, I don't like the default color at all. Ugly brown. So here we go. We have this triangle. And in the first section, we learned how to parametrize a triangle. Okay, But we can do it in an easier way because we know how to think of it as a Cartesian surface. Okay, so that triangle is above another triangle. Ooh, oh yes, because here's the x-axis, here's the y-axis. Seen from above, okay, we ignore the z-coordinate. We are on top of the origin. We are on top of 3, 4, which is over here. And we're on top of 0, 4 over here. Oh, look, it's a right triangle, okay, because we have the same y-coordinate over there. Okay, so we can write this as a type 1 or a type 2 region. Oh, you know what? I think type 2 is going to be easier, okay, because all we need to do is find the equation of this line. We'll go from 0 to that line. Okay, so I think let's do it that way. Okay, so we will treat this triangle as a Cartesian surface above the triangle. Sorry, it was the origin, and then 0, 4 on the y-axis, and 3, 4. Okay, which will be the domain of our double. I better put it on the next line because it can keep going. Domain of our double integral. Okay. So what are we gonna do? Maybe find the equation of plane first. Okay. And luckily we are passing through the origin, so all we have to do is take the cross product of these two points. Vectors treated which correspond to those points. Okay, so if we put them on top of each other, I believe you remember the trick to find the cross product. Okay, so we will get the normal vector. So that will be the vector. Let me write it as 1 by 3. So we get 8 minus 0, so that's 8. And then 0 minus 6, so that's minus 6. And then 12 minus 0, so that's 12. So I guess we can divide everything by 2, right? So we will have as our normal vector 4, negative 3, 6. Okay? So the plane has equation 4x minus 3y plus 6z equals 0 because we are passing through the origin. Okay, so let's double check in GeoGebra that we have the correct equation. All right, here's our plane. 4x minus 3y plus 6z is 0. And are we correct? It looks like... Yeah, it looks like I didn't make a mistake for a change. Okay, excellent. So, because we're treating this as a Cartesian surface and our domain is on the xy plane, we are going to solve for z to create our parametric. Okay, so we said that we're going to treat this as a type 2 domain, this triangle that we're going to use to parametrize our surface. So we will have u going from 0 to 4, 0 to 4, and then v will go from 0 to the line connecting the origin to 3, 4. So that would be, so u is our y. So the equation would be u equals, what's the slope? 4/3. 4v over 3. So solving for v, v is 3u over 4. Okay, so v is going from 0 to 3u over 4. Okay, so that is our parametrization. Yes, okay, yeah, the slope is 3 over 4. Okay, makes sense to me. All right, so we have this plane, and we said we need to solve for z. So z is 1/6 of, what are we going to get? Negative 4x. So the x is the v, and plus 3y. The y is the u. Okay, so that is our z. And so therefore we have r of uv. I need braces. Okay. So r of uv will be, okay, so u is going from 0 to 4. V is going from 0 to 3 u over 4. And then our, oh wait, and, almost, and you're going, wait a minute. Yeah, the u is the y, okay, the v is the x, and the z is minus 4v plus 3u over 6. Okay, and this is our domain. Yes, I'm just going to copy that down. Okay, so we are ready now to plug in the density. Plug this into. Here we go. So we will get 5x, so that's 5v, plus 6y, so that's going to be 6u, plus z, plus 1/6 of this. Okay, so simplify that. What are we going to get? We're going to get that as our integrand. Okay, so we also need the RU, the RV, and we're going to take that cross product and find the length of that cross product. Okay, so we have, oops, stop that. We have this, and we will take the partial derivatives. Okay, give me space. We need R sub U. Okay, so R sub U. Who are you? V disappears. U becomes 1. Okay, we have V disappears and we get 3 over 6, also known as 1/2. Okay, that is our R sub U. How about R sub V? So we get, be a little closer. Who is R sub V? Okay, so this time V turns into 1, V disappears, we get minus 4 over 6 for R sub V. That's minus 2/3. Minus 2/3. Haha. Okay, there we go. So we need the cross product. This cross with this. Okay. So what are we gonna get? Blank this out. Too dangerous. Okay, so we get minus 2/3 0. Okay, 1/2 0. And then 0 minus 1. Okay, so finally, we need the length of this cross product. There's my length. How long is this vector? So we have the square root of, whoops, not fraction, silly, this one. We get 4 over 9. Now we need a fraction. And then 1/4, and then 1. Okay, so LCD of 36, so I think we're going to get a 6 in the denominator. There you go, 1/6 square root of 61. So 16 and 925 plus 36 is 61. All right, so that is our length. We're now ready to find the mass. Mass of S is. Okay, let's bring back our parametrization. Okay, let's over here, because we need that in order to set up our double integral. Okay, so we need on the outside u going from 0 to 4. Okay, so we have du on the outside, and we have dv on the inside. Okay, so we have v integrated from, subscript, v equals 0 to v equals 3u over 4. Okay, what are we integrating? Do not forget to include this. We worked for that, all 2 minutes of it. And we have the function that we are integrating. Okay. Oh, wow. 13 in common. Score. So we have this. Okay. Yeah. We're back to chapter 2. Okay. And this one is not very difficult. Okay. You sure you don't want to do a triple integral? Good times. For me, not for you. So, let's see. We can take out the 13 and this. Yeah. So, yeah, you know what? Let me do this. So, let's take out 13 over 6. Okay, and that ugly radical. So, take that out. And we have 1/2. 1/3. Okay. Let's do a little cosmetic surgery first. All right, and then what do we have? Okay, we will integrate with respect to v. So we get an extra v here, and we get a v squared over 6. Okay, v has been integrated. We will go from v equals 0 to v equals 3 over 4. Okay, so those are our endpoints. There we go. So 0, thank you, you go away. And for the upper endpoint, you multiply by 3 over 4 v squared. We're going to get 9u squared over 16. 9u squared over 16. Okay, excellent. So that's going to reduce it. Oh, look. We got u squared here. So something nice is going to happen. Yes, we're going to get, yeah, just 15 over 32 u squared. Excellent. So, yeah. Oh, yeah, by the way, we don't need that anymore. We already plugged that in just to check our grammar. So therefore, this is going to be our outer integral. Excellent. So that one, yeah, easy to do. We simply have, take this outside. Wait, actually, you know what? U cubed over 3, so that turns into 5. Yeah. And we will go from u equals 0 to u equals 4. Yeah, there we go. So, oh, and something else is going to happen. 4 cubed, 16, 64 over 32, that's just times 2. Okay, so therefore we are going to get times 10. Is that right? Yeah, 64 over 32 is 2 times 5 times 10. Yes, we get this as our final answer. Okay, there you go. So that is the surface integral of a scalar function. There's one more example in the book, And that involves a surface which can be parametrized using polar coordinates. Okay, so I will leave it to you to read that example. In our next video, we're going to look at the flux integral of a vector field across a surface. Right? So until then, enjoy the rest of your day. I will see you very soon. Bye.